Hello, students, wherever you are. Today we are learning double titration. Double titration, we have finished back titration. We are now starting a new type of titration called double titration. In double titration, we have three solutions. One is organic acid like citrus acid and phosphoric acid, citrus acid, methanoic acid, butanoic acid, and many other acids. These are acids that are obtained from plants and animals product. So we call it organic acids. So we have also another acid called inorganic acid. Inorganic acid. These are acids that are manufactured by human beings. An example like hydrochloric acid, like nitric acid, like phosphoric acid, and many others. So this one are manufactured from industries. We call it mineral acids. We have also a base which is sodium hydroxide solution. Which is a base. We have these three solutions. Double titration involves three solutions: organic acid, inorganic acid, and base which is sodium hydroxide. So the base can be potassium hydroxide, lithium hydroxide, any hydroxide of any group 1 element. It's not must be sodium hydroxide only. So in the first place, you react the organic acid and the base. Then you fill the first table. This is called for procedure 1. You fill the first table. Then after that you do the calculation. Then the next is you take the base again, you react with the inorganic acid. Then you do the second calculation and you fill the second table, and that's procedure 2. So that's why this double titration is from that point. Double means there's 2 times that you are titrating a base with 2 different acids, organic acid and inorganic acid. Okay, let us start without wasting any time. You are provided with solution A, which is hydrochloric acid, solution B, sodium hydroxide, solution C, dibasic acid, H2A. We don't know that compound, containing 2.223 gram in 250 centimeter cubic of solution. Then we have procedure 1. Fill the burette with dibasic acid. Using a pipette, place 25 centimeter cubic of sodium hydroxide solution in a clean conical flask. Then you add 2 drops of phenolphthalein indicator. Then you fill the table. So final reading 30, 30, 30. Initial 0, 0, 0, 0. So volume of dibasic acid used is 30 centimeter cubic, 30 centimeter cubic, 30 centimeter cubic. Here is 2, 30, 30, 30, 30. So now when we go to the calculation part, first question is asking calculate the average volume of dibasic acid. So calculate the average volume of dibasic acid. To calculate the average volume, this is what you do. You add all of them, all the 3. You add all these 3. 30, 30, 30. So then you divide by 3. This is what you do. 30 centimeter cubic plus 30 centimeter cubic, 30 centimeter cubic plus 30 centimeter cubic plus 30 centimeter cubic divided by 3. When you add all of them, you'll get 90. 90 divided by 3, then you'll get 30 centimeter cubic. So 30 centimeter cubic is the volume of the dibasic acid used. So that's how you get Roman 1. So Roman 2, it's asking calculate the concentration of the dibasic acid in gram per liter. So to calculate the concentration in gram per liter, we have learned also that one, you get the mass. The mass of the dibasic acid is this one, 2.223 gram. The total volume is 250. So mass is equal to total volume with about 1000. So 2.223 gram is equal to 250. Then what about 1000? Then you cross multiply this one, you multiply this one, you multiply this one. Then here you'll get 1000 times 2.223 times 1000. Then divide by 250. When you do that, you'll get 8.9 gram per liter concentration. So that's how you calculate the concentration of the dibasic acid in gram per liter. So again, question Roman 3, we have the concentration of the dibasic acid in moles per liter. Concentration in moles per liter means molarity. You use this formula. Molarity is equal to concentration in gram per liter over RFM. So concentration in gram per liter of the dibasic acid already you have, it's here. So you only calculate the RFM. RFM, how do you calculate? They give us in the compound of dibasic acid with H2, C2, or 4, where C is equal to 12, H is equal to 1, and O is equal to 16. Then we calculate the RFM. RFM is of this compound H2, C2O4 is equal to hydrogen in the bracket 1, we have 1, then we have 1, and here we have 2 hydrogen. So that means 2 times 1 plus carbon, we have 2 carbon here, and here in the bracket we have carbon 12. Carbon we have 12. So 2 times 12. Then plus 16. Oxygen here is 16 in the bracket, 16. 16 times 4. Why am I saying 4? Because here we have 4 oxygen. Then 2 times 1 is 2. And then 2 times 12 is 24. Plus 16 times 4 is 64. When you add all of them, you'll get 90. Then molarity therefore is equal to concentration gram per liter over RFM. Then my concentration is 8.9 divided by 90. I will divide 90. Then I'll get 0.1 molar of dibasic acid. That is the concentration of the dibasic acid in Roman 3. So we have Roman 4. Roman 4 is asking the number of moles of the dibasic acid. To calculate the number of moles of the dibasic acid, you have the molarity here. This is the new molarity that you have obtained, 0.1 molar. You have also the volume used of the dibasic acid. This is the volume used. So then you will say this molarity is equal to 1000. What about 30? So let us see in the next page that question. 0.1 mole is equal to 1000. 30 centimeter cubic, how much? Then you cross multiply. This one you multiply this one, then you divide 1000 because 1000 is multiplied x. 0.1 molar times 30 centimeter cube divided by 1000. When you do that, you will get 0.003 moles of the dibasic acid used. This is the number of moles of the dibasic acid used. So the next question, which is Roman. This is Roman. The next question, which is Roman. This is the number of moles of the dibasic used. So Roman 5, let us see Roman 5. Roman 5, it's asking the number of moles of the sodium hydroxide used. If we have the number of moles of the dibasic acid used, to get the number of moles of sodium hydroxide used, you react, then you balance the equation, and this is what you do when you are reacting. Sodium hydroxide solution plus H2X. Why am I taking X? The compound was H2A. I pick it A, I pick it Y. You can take A, you can pick Y, you can take X, any letter. But provided that this acid is dibasic. A dibasic acid always contributes a radical of valence 2. For example, you have learned in Form 2 that if the acid has 2 hydrogen, like sulfuric acid, it has a salt of sulfate. And that sulfate has a radical is valence 2. It has valence 2. If you have hydrochloric acid, it has 1 hydrogen. So if it has 1 hydrogen, we call it monobasic acid. Monobasic acid always contributes a radical of valence 1, which is chloride. If we have carbonic acid is a dibasic acid. It has 2 hydrogen. Since it has 2 hydrogen, it contributes a radical of valence 2. So since our acid is valence, it has 2 hydrogen, then we expect the radical either A or Y, any letter you can take it, that compound of the anion that it contributes, or the radical that it contributes, has valence 2. So now Y has valence 2. Then when we react sodium hydroxide with this acid, this is what we get. Sodium 2Y, which means valence 2. Y has valence 2 contributed to sodium, where sodium has valence 1. Then this is how you write. Y sodium 2Y, then plus water, because this is a salt reacting, an acid reacting with the base, and the product is salt plus water. Okay, now let's balance the equation. Sodium here 2, sodium 2 here. Balance. Sodium 2 here, sodium 2. Y1. Okay. Hydrogen 2, hydrogen 2. Then oxygen 1, oxygen 1. It's balanced. Mole ratio is 2 to 1. Then if the number of moles of the dibasic acid is 0.002, 1 mole ratio is equal to 0.002. 2 mole ratio, how much? Then you cross multiply. Then this is what you will get. This is what you will get. 2 times this one, then you divide 1. Then you get 0.006 moles of the sodium hydroxide used. So this is the number of moles of sodium hydroxide used. So let us see Roman 6. Roman 6 is asking the concentration of the sodium hydroxide solution. Now to get the concentration of sodium hydroxide solution, this is what you do. Sodium hydroxide solution, the volume used is 25, and this is the number of moles of sodium hydroxide used. So the number of moles of sodium hydroxide used is equal to the volume used, which is the pipette volume. This pipette volume, if I go back, I will show you. Here we have, using a pipette, place 25 centimeter cube of sodium hydroxide. This is the volume used. Then the number of moles of sodium hydroxide used is here, 0.006. So therefore, 25 centimeter cube is equal to 0.006, what about 1000 to get the molarity. Molarity in terms of volume is equal to 1000. Then you cross multiply, you will get 0.24 molar of sodium hydroxide. So that's what you will get. Then that's the end of procedure 1. We have procedure 2. Procedure 1 was involving a reaction between organic acid, which is dibasic acid, and the base. Again, we have procedure 2. Procedure 2 is saying, using a measuring cylinder, 100 ml measuring cylinder, measure 10 centimeter cubic of hydrochloric acid, and add distilled water up to the mark, and label as solution F. So you add distilled water up to the mark and you label solution F, not solution F. Here is solution R. Yes, solution R. Then fill the burette with solution R. The new solution that you have prepared, you fill the burette. Then using a pipette, you place 25 centimeter cube of sodium hydroxide solution in a clean conical flask. Then you add 2 drops of phenolphthalein indicator. Then you carry out the titration. Then you fill the table. Now when you fill the table, here you are reacting hydrochloric acid and you are reacting the base. Where the first procedure was, you are reacting the organic acid and the base. So the average volume, calculate the average volume. Average volume, you add all these 3. 20, 20, 20.0, 20.0, 20 divided by 3. Then 20, 20, 20, when you add the 320, 60 divided by 3, you get 20 centimeter cubic of hydrochloric acid used. So we have Roman 2. Roman 2, calculate the concentration of hydrochloric acid in moles per liter in 100 centimeter cubic. To calculate the number, the concentration or the molarity of hydrochloric acid used, this is what you do. First you have to calculate. You start because hydrochloric acid, you have nothing here. There is nothing that you have here. If I go back here, the hydrochloric acid in the first procedure, they only give us a plain hydrochloric acid. They have not given any mass. They have not given us any volume. So the only way that you can calculate hydrochloric acid's molarity is by using the other solution that's been reacted with, which is sodium hydroxide. So first you calculate the number of moles of sodium hydroxide by saying like this: the molarity of sodium hydroxide that you have obtained in procedure 1, which was 0.24, is equal to 0.24 is equal to 1000 centimeter cubic. What about 25? 25 is the volume of sodium hydroxide used according to using a pipette, place 25 centimeter cubic of sodium hydroxide. What about 25? Then you cross multiply. When you cross multiply, 25 times 0.24 divided by 1000, then this is what you'll get. This is the number of moles of sodium hydroxide used when reacted hydrochloric acid. So now to get the number of moles of the acid used, you react equation. You react sodium hydroxide with hydrochloric acid, then you get sodium chloride plus water. Then the mole ratio is 1:1 because this equation is balanced. Then if the mole ratio is 1:1, the number of moles of hydrochloric acid will be the same with the number of moles of the base, which is 0.006 moles. Then when you have this number of moles is the number of moles of the hydrochloric acid you used. We have also here the volume of hydrochloric acid used, which is 20. Then in the next page, this is what you do. 0.006, which is the moles of hydrochloric acid used, is equal to 20 centimeter cubic. What about 1000? The molarity, X, you don't know. You cross multiply, then you divide by 20. 20 will go down, it will divide it, then you'll get 0.3 molar, the molarity of hydrochloric acid. Then the next question is asking, calculate the original concentration of hydrochloric acid used. Since we have the concentration of the acid, final concentration, since we have the final molarity, we can calculate the original by using this formula. M1 V1 is equal to M2 V2, where M1 we don't know, V1 was 10 centimeter cubic, M2 is 0.3, then V2 is 100. Then you use the formula, you substitute